Okay, so here's the plan. My goal is to finish covering this section on convergence analysis today, and then, assuming that happens, then there will not be class Wednesdays. My other class on Wednesdays is already canceled for every reason. And after that, there's not much left. So I'm going to remove section 12.6 from the schedule because there are no homework problems on it. Although, actually, I want to check. I don't remember if I put a quiz on it. I didn't think of that. Let's see. Oh, there's no quiz on it either. Okay. So, yes, section 12.6, gone. It's not a very interesting section anyway. After that, there will be sections 13.1 and 13.2 that I need to cover. So for those of you who choose the coding option for the final, it'll be on those sections on boundary value problems. So I will start covering those sections next Monday. Once I finish those sections, we don't meet anymore. So, now, I do have the day on the schedule that's set aside for it's called Final Project Discussion, currently May 4th, the last day of classes. So if we have a non-empty subset of students of the class that chooses the coding option, then I will use a class period to handle any questions about that. Otherwise, that's it. So we're beginning to wind things down. Okay, so never mind. Continue with convergence analysis. So what I covered last time was how to show that a one-step method or a multi-step method was consistent, meaning that the local truncation error goes to 0 as time step size h goes to 0. I also showed how to prove that how to establish that a one-step method is stable, meaning that the difference in two solutions is bounded by a constant independent of h times the difference in the corresponding initial values. So a slight change in the initial data does not lead to an unduly large change in the computed solution. So what's left? I need to show you how to establish stability or lack of stability for a multi-step method. And then I'll just discuss convergence in general. Also, the concept of a stiff differential equation and ramifications of that. Okay. So, fortunately, it turns out, through a lot of theory that was established long ago, to be surprisingly easy to check whether a multi-step method is stable. In fact, it's easier to do so than for a one-step method. Because with a one-step method, you have to show that the function phi that defines your one-step method is Lipschitz discontinuous. And how easy or difficult that is depends on the particulars of a function phi. Not so for multi-step methods. They all have this form. So there's a uniform approach to check on stability. So what we're really looking for is to determine whether it's 0 stable. I'll explain what that means right now. And so that this relates to the simplest ODE of all, y prime equals 0. So, of course, the solution is a constant. It's just equal to the initial value. So, when you apply this multi-step method to this ODE, then it reduces to this. Because the whole right-hand side deals with a function f. Function f in this case is 0. And this is a recurrence relation that you would solve for values of y. There are n plus 1 terms in the sum, so it's called an n plus 1 term recurrence relation. So, and this is something that we know how to solve. So to solve this recurrence relation, we consider what is called a characteristic equation of a recurrence relation. And it comes about from assuming that like yn is equal to lambda to the n for some value lambda. So making an assumption in here leads to this polynomial equation. So what we do is we find the roots, lambda, of this equation, so m roots in all, the polynomial degree m. And then we have a formula for a solution in terms of those roots. So here we have whatever roots you get, lambda 1 up to lambda m, are raised to the nth power, to get yn. And you might have powers of n here. It depends on whether any of the roots repeat. This is kind of like what you would have learned about in your first ODE class. Like with second order ODEs, you're solving a characteristic equation like this one, and you get your roots. And normally the solution of your ODE would be exponentials, like e to the x, e to the 2x, something like that. And then, if there's a repeated root, you'd have a factor x e to the 2x. Hopefully it rings a bell. It's the same thing happening here. So these powers of n occur when you have repeated roots. Right. Now, and then the constants, the CI here, those are determined by the initial conditions. But in this case, we're not particularly concerned about any particular initial condition. What we want to know is, we want to make sure that whatever roots we have, that this solution will not grow over as n increases. So as n goes to infinity, we need to make sure the solution decays to 0 or becomes stationary. That would be fine too. All right. So how can we ensure that? Well, that depends on the roots. So if the roots are less than or equal to 1 in absolute value, and for any roots that have absolute value equal 1, keep in mind these roots could be complex. So we're not talking about just plus or minus 1. Then it must be a simple root. It cannot be a repeated root. So under these circumstances, this solution will not grow as n goes to infinity, which is how you would expect the solution to behave, because the solution, the exact solution, is constant. We want the computed solution to therefore at least not grow. So as long as the roots satisfy this property, which is called a root condition, then that would be the case. So we therefore say that the multiset method is 0 stable if and only if it satisfies the root condition. Now there's two kinds of 0 stable: strong and weak. So strongly 0 stable if the only root that sits on the unit circle, the only root of absolute value 1 is 1. Otherwise, for example, if you have plus or minus 1 as roots, then we say it's weakly 0 stable. Lambda equals 1 is always going to be a root. And the reason why is to satisfy the various conditions of consistency that I laid out last time. One of those conditions is that the alphas have to sum to 0. So So if the alpha is always summing to 0, it means that 1 is always going to be a root. Okay. So here's an example. With the Adams method, we have, here's a characteristic equation, and this comes from the fact that for an Adams method, we always have yn plus 1 minus yn equals whatever right-hand side is. So in this case, when we're applying the ODE y prime equals 0, this reduces to yn plus 1 minus yn equals 0. In other words, alpha 0 is always equal to 1, alpha 1 is always equal to minus 1, all other alphas are equal to 0. So this is the characteristic equation. Well, here we can easily get the roots. We have 1 as a simple root, and then we have 0 as a very often repeated root. So, because 1 is the only root of absolute value 1, an Adams method is always strongly stable. Any questions so far about the root condition? Now here's another example. The Simpsons method is a, oh, wait a minute. Why are we not scrolling? Scroll. What are you doing? Yeah, I'm totally scrolling up and down right now, and this is doing nothing. Okay. I don't know if I'll have it if I wait long enough. Or, okay, I think I'll stop sharing. Oh, we're having problems connecting to the network. No bleep, Sherlock. Okay. All right, I'll try stopping sharing and share again. And it's not doing anything. Okay. All right, I'll try. Oh, now it's hanging. Oh. Not sure what happened there. Oh, wait. All right, better. Okay, it's scrolling with me now. Okay. Here's the method I was trying to show you. Simpson's method is another multi-step method. It is neither an Adams method nor a backward differentiation formula, the BDF that I showed you last time. So, it's a very unusual multi-step method. It doesn't fit into either one of those baskets. And you can kind of see the resemblance to Simpson's rule for numerical integration, where the middle value is given 4 times the weight of the values on either side of it. Notice also, instead of y plus 1 equals yn plus something, it's yn minus 1. So, alpha 0 is equal to 1. Alpha 2 is equal to minus 1. And all of our alphas are 0. So this is a characteristic equation, and the roots are plus or minus 1. So because there are 2 roots of absolute value 1, Simpson's method is weakly 0 stable. And then it has been proven that if you have a backward differentiation formula for m greater than 6, that that it's always going to have either a root that's outside the unit disk, so absolute value greater than 1, which is a total no-no, or having a repeated root that sits on the unit circle. So it is always 0 unstable in that situation. So that's why these kind of vector differentiation formulas that are very high order cannot be used. Okay, so that's all you have to do to check stability of a multi-step method. Now, the thing is, if we consider what I mentioned last time, the definition of stability for any time-stepping method, that the different, and I reiterated at the beginning of today, but the difference between two computed solutions is bounded by the appropriate constant times the difference in the initial data. I haven't said anything about that for multi-step methods. However, it has been proven, and there's a, okay, I'll just make a note of it here. Oops, stop that. Has been proven, and it's a really old numerical analysis text that I also find quite useful, by Isaacson and Keller, that a zero stable multi-step method, whether strongly or weakly, fulfills the definition of stability. So you don't have to try to prove directly that a multi-step method satisfies that original definition of stability. You just got to show that it satisfies a root condition, and then it's known by what Isaacson and Keller proved, that it is stable in the sense of that original definition. By the way, I actually knew Keller. Keller refers to Herbert Keller. Joe and Herb Keller were brothers, and two extremely prolific applied mathematicians. They were both at NYU for many years, and then Joe Keller went on to Stanford, where he served on my dissertation committee. And I often refer to him as the world's foremost living applied mathematician at the time. He passed away not too long ago. And then his brother Herb was a professor for a long time at Caltech. Quite geniuses and also quite entertaining personalities too. Okay. Actually, I and my fellow graduate students were always very scared of Joe Keller. He was pretty harsh on us. But, okay. Now, all right. So that covers stability. So for one-step methods, you show the 5 functions satisfies the Lipschitz condition. For multi-step methods, you check the root condition. So now that we know how to check whether a one-step or multi-step method is consistent and how to check whether it is stable, we get to what we're really after, showing it as convergent. So, in a nutshell, you want consistency and stability. So, if you show that such a method, one-step or multi-step, is consistent and stable, then you know that it is convergent. For multi-step methods specifically, you can make a slightly stronger statement. If it's consistent, then it's convergent if and only if it's zero stable. So what I said earlier was zero stable implies convergence, but convergence also implies zero stability. And this is a theorem called the Domquist Equivalence theorem. So German Domquist has several very important convergence theorems related to multi-step methods, and I'll mention more of them a little bit later. The lax equivalence theorem for one-step methods is, for one-step methods is a theorem that states that consistency and stability imply convergence. Now, I can actually show you how it works for one-step methods. So let's suppose that a one-step method has ellipsis constant, because that would give stability. And compared to last time's notes, I'm simplifying things a little bit. I'm making one Lipschitz constant that applies to the y argument, yn argument, and the yn plus 1 argument. Really, I'm just taking the maximum of the two Lipschitz constants that I had before. Because before I had L1 and L2. So L phi is just the max of L1 and L2. So we established this, that gives us stability. Now, for h sufficiently small, in other words, bounded by h naught that's defined to be equal to this, and I give it a definition of delta last time, then we end up with this. So this I derived last time. The only difference is, again, replacing L1 and L2 by L phi. Okay. Now, when we show convergence, I had actually shown you convergence specifically for Euler's method back in now section 12.2. I can follow the same proof, so the same general argument. So for that, I define the error after n time steps to be the difference between the computed and exact solutions. And from the fact that the one-step method in question is consistent, I have that the exact solution satisfies the equation defined by the one-step method, except for this additional term, h times the local truncation error, tau n of h. So now, by putting this inequality and this equation together, I get this. So this is essentially this inequality all over again, except I have this extra term that takes into account the local truncation error. So now, this relates the error after n plus 1 time steps to the error after n steps. If I apply this repeatedly, then this is what I get. And the details of how you get from here to here, it works out exactly the same as how as in the convergence proof of Euler's method. So all the algebraic manipulations, like we end up getting a geometric progression and using a formula for that. All of that plays out exactly the same to get you from here to here. And what this shows is that because the method is consistent, we know that this goes to 0 as h goes to 0. This is a constant independent of h. So as h goes to 0, this whole thing goes to 0. So therefore, the method is convergent because we see the global error, the difference between the computed and exact solution, going to 0 as h goes to 0. So this is how. So to establish that, I relied on consistency, and then stability is what the one-step method is what gave me this in the first place. Because I couldn't get this without knowing if phi satisfied this Lipschitz condition. Questions about this? referring to last time's notes because that shows you the algebra that was used to get from here to here. So falling back on all kinds of old things. Now, this is just determining method convergence at all. What about if you know method convergence, but you want to know what's the order of accuracy? That if method is consistent and stable and therefore convergent, the global error has the same order as local truncation error. Which is actually why the local truncation error is defined the way that we do, where we rewrite the numerical method in a way that mirrors the ODE, where we're dividing both sides by h. So that convention to define consistency in that way makes it convenient that all you got to do is figure out what the order of a local truncation error is, show that the method is also stable, and then you know what the order of magnitude of a global error is too. Okay. Now, concept of stiffness. This is what this creates quite a challenge for numerical methods for ODEs, and therefore PDEs that rely on these methods. I've actually seen different definitions of stiff. But one way to describe a stiff problem is this. So stiffness is a problem of the underlying problem, the ODE itself, not the numerical method used to solve it. So one definition I give here is that if the exact solution, that's yt, has negligibly small terms that decay to zero, t goes to infinity, like decaying exponentials, but have very large derivatives. So this is an example, if the exact solution has a term like this, e to the minus ct, where c is a large positive constant, then you take the derivative of this, and it's magnified by that constant. So even though e to the minus ct itself is small, derivatives can get very large. Another definition of stiffness is that the time step needed to compute the solution is much smaller than the time step needed to accurately represent a solution. In other words, the solution itself might be very smooth, meaning you only need to evaluate it a few times to obtain an accurate graph of it. But using that larger time step might make it possible to compute the solution using a time-stepping method. Now, the reason why large derivatives are a problem is because anytime, if you look at the error formula for a one-step or multi-step method, it has a higher order derivative in it. So if your solution has large derivatives, even if your error includes a factor h to the p, where p is large, thinking, oh, this is a very high order accurate method. If the derivative is very large, then your error is still large, even though it's a high order accurate method. So we can't ignore this factor that appears in the error terms. So the consequence of this in practical terms is that to compute the solution of such an ODE, you generally need to use a much smaller time step than you would for non-stiff problems. So your computational expense increases because you're having to take more time steps to get from your initial time to your final time. Oh, so here's the other notion of stiffness that I gave. Again, the time step needed to compute solution is much smaller than the time step needed to depict a solution. So, and the problem is, a lot of ODEs come from PDEs. You have a PDE that deals with spatial and temporal variables. You discretize the PDE in space only, and now you have a system of ODEs. Such systems are generally stiff. So this is a big problem. Okay. So here's an example. Y prime is minus 100y. So we have a large constant here. You have the exact solution, decays to 0 very rapidly. So we go ahead and apply Euler's method to this ODE. So our function f is minus 100y. So we fill that in here. So now we have this simple relationship between yn plus 1 and yn. We're just multiplying by 1 minus 100h. So let's pick a reasonable time step. H is 0.1. Well, then you work that out, and this is your formula for y sub n. It's minus 9 to the n. Well, that's going to grow. It's going to grow and oscillate. Totally wrong behavior. Solution is supposed to decay to 0 rapidly. This is the total opposite of that. All right, fine. Choose h equal 0.001. Now we have 0.9 to the n. At least it's decreasing now as n increases. It's decaying instead of growing. But still not fast enough. Really should have an even smaller h to get a reasonably accurate solution. So get an idea as to what a reasonable h would be to ensure correct qualitative behavior of a solution. Instead of using y prime equals 0, like for zero stability, we use another simple ODE called the test equation. Y prime equals a constant times y. And we assume that the constant is a complex number with negative real part. So that the solution is supposed to decay to 0 as t increases. The exact solution. But if the real part is large in absolute value, then the ODE is stiff. So it has that rapid decay to 0, but solving this ODE numerically is going to require a very small time step, much smaller than you would need to produce a proper graphical solution. So how do we find a reasonable value of h for a one-step method? Well, what happens is, if you plug in an ODE this simple into your one-step method, you get an equation of this form. Q plus 1 is some function of h times lambda applied to yn. Now, what kind of a function is this? It depends on whether one-step method is explicit or implicit. If it's explicit, it's a polynomial. If it's implicit, it is a rational function. Either way, it's supposed to be an approximation of the exponential, e to the lambda h. That's what happens to the exact solution. You get from yn to yn plus 1. The exact solution, you multiply by e to the lambda h, or h lambda, whatever. The exact solution exhibits exponential decay. So this needs to be true. So we can analyze this function that comes based on the one-step method and require that it has this property from a test equation. And that gives us an idea of how small the time step needs to be in terms of lambda. So now I'll show you how that works out for certain one-step methods. So here's an explicit method, explicit Trapezoidal method, also known as modified Euler method. So here's the method itself. So if I substitute, f is equal to lambda y, then this is what I get. Can anyone tell me, how does this function here, how does that relate to the exponential e to the h lambda?
Taylor series?
Yes. We actually have a first three terms of the Maclaurin expansion of e to the h lambda. That's why this is a second order accurate method. But we need to make sure that this has absolute value less than 1. So, okay. So what I do is, I'm going to let x equal h lambda, just for notational convenience. So I want this to have absolute value less than 1. In other words, it's between -1 and 1. So now I have this set of inequalities. Now, so to make sure this happens, okay, so now I have this inequality just from canceling out the 2's. Okay. Now, so from looking at this inequality, this has to be negative for one thing. Because, oh, hold on. Okay, sorry. This inequality leads to this one, and this inequality sorry, I'm not paying attention to my own notes. Okay. That's the end of the day. Okay. So, what happens here is, from this inequality over here, since this has to be negative, so these have to have opposite signs. Now, first of all, x is equal to h lambda. Now, h is a time step, so that has to be positive. Lambda is assumed to be a number with a negative real part. So x, therefore, is negative. So for this whole thing to be negative, we need this factor, 1 plus x over 2, to be positive. Okay. So from that means that x must be less than what thing's going to be wrong? It should say be greater than -2, not less than. I knew something was wrong there. So h lambda actually has to satisfy this constraint, that an absolute value must be between 0 and 2. Now, what this means is, because there's a product of h and lambda, the larger lambda is, the smaller time step must be. A consequence of this is, when you're using time stepping methods for ODEs to solve spatially discretized PDEs, more spatial resolution you use in your PDE, the larger values of lambda you get, therefore the smaller the time step must be. In other words, typical methods for solving time-dependent PDEs are not scalable to higher resolution. You increase your spatial resolution, your computation time goes up considerably, like in a quadratic fashion, because of circumstances like this. Okay. So questions about what happened here with this method? And the Euler's method has a similar constraint on the time step. Now for a multi-step method, if you apply it to the test equation, you get a different recurrence relation from before because now we have this coming from the betas. Now, from this recurrence relation, we get what's called the stability polynomial. It's a polynomial in it's a polynomial in the variable mu, but h lambda is a parameter that affects the coefficients. So for each choice of h lambda, you get a different polynomial. Now, we want our y's to exhibit exponential decay. Therefore, the solution of this recurrence relation must decay to 0. Now, we saw this situation before in the case of zero stability, where we needed the roots, in that case, to be less than or equal to 1 in magnitude. In that case, we wanted to avoid growth. Here, we don't even want growth. We want decay, only decay. That means the roots of this polynomial must be strictly less than 1 in magnitude. And that's the condition stated here. So for whatever values of h lambda you specify, then you have this polynomial degree m. You get its roots, mu1, mu2 up to mu-m. Check whether you want to make sure that all the roots have absolute values strictly less than 1. Then, the solution of this recurrence relation, the yn, will decay exponentially. Here's an example involving Adams-Bashforth method. So a 3-step method. So here's the stability polynomial. That is determined partially by these coefficients of the Adams method. And we have a value, a parameter h lambda appearing in various spots. Now the thing is, here, once you pick an h lambda, then you have to get the roots numerically. So there's no nice formula to determine the stability constraint in this case. So I'll just do some examples. I'll let lambda equal minus 100, so that's a nice stiff ODE. If I choose h equal 0.1, we get a large root. So the method is definitely unstable in that case. It will not produce a right solution. If I choose a much smaller time step, 0.005, then all the roots are small enough. Remember, the larger the value of lambda in absolute value, the smaller the h you need to get correct behavior in your solution.
How do you choose lambda again? Or is that just all?
Oh, I just spit it up.
Okay.
Yeah. So the thing is, let's suppose if I chose lambda equal to minus 1,000, then this would have to be smaller by a factor of 10. Because this polynomial depends on the product lambda times h.
Right. Yeah. And we want mu small.
Yeah, we want the roots mu to be small.
Or at least in magnitude.
Yes.
Yeah, okay.
Okay. So, trying to find for which values of h lambda we get small enough roots leads to the concept of a region of absolute stability. So region of absolute stability is a subset of the complex plane. It's defined to be the set of all complex numbers h lambda that work for your method, meaning that they produce an exponentially decaying solution. So if your method that you're studying is a one-step method, you're trying to find all h lambda that satisfy this condition. If your method is a multi-step method, you're trying to find all values of h lambda for which this polynomial has roots less than 1. Actually, this should not have absolute values in it. Okay. Not sure what it's doing there. And of course, I'm going to make sure I didn't do it in the book. Okay, I did not. Well, that's a relief. Actually, in the process of preparing these notes, or really these are the same notes I used last time, only updated, I found that there was a mistake in these notes, and fixing that led to realizing that something I had in the book that I thought was wrong turned out to be correct. Okay, so in case of multi-step method, this polynomial must have roots less than 1 in magnitude. So you find all complex numbers h lambda for which this occurs, for whichever method you're studying, and that gives you a region of absolute stability. And I'll call that R. Now, the ideal situation is that your region of absolute stability R includes the entire left half plane. So in other words, for any lambda you choose with a negative real part, you can choose any h you want, and it'll be in the region of absolute stability. That's called an astable method. So that means for methods like that, you don't have to worry whether your time step is small enough, at least for stability's sake. Now, you want a small enough time step to ensure accuracy, but you don't have to worry about your solution behaving incorrectly. Like, you don't have to worry about your solution blowing up on you when it's supposed to decay. Backward-Euler is an astable method. So here it is applied to the test equation. So now I rearrange to isolate yn plus 1. So yn plus 1 is equal to this value times yn. So this part in parentheses is your function q of h lambda. But lambda has a negative real part. So the real part of a denominator is going to be greater than 1. A positive number greater than 1. It's not just greater than 1 in magnitude. That means this complex number, 1 over 1 minus h lambda, will always be less than 1 in magnitude. So this method is also called unconditionally stable. In this case, it's an astable method. Its region of absolute stability includes the entire left half of a complex plane. It can also be shown that the implicit trapezoidal method, which is the average of backward-Euler and forward-Euler, that is also astable. What happens in that case is your numerator is 1 plus 1/2 h lambda. The denominator is 1 minus 1/2 h lambda. You can show that that fraction also has magnitude less than 1 whenever lambda has a negative real part. So there's a couple methods that are astable, but generally methods are not. In fact, we have this theorem, these theorems that from Domquist that impose constraints on multi-step methods. He has 2 barrier theorems. So the first barrier theorem is that anytime you have a zero stable multi-step method, there's a limit, there's a ceiling on its order of accuracy. So if it's an m-step method, this is the maximum order of accuracy that it can have and still be zero stable. And I think I have an example. No, I don't. I'm not going to mention it in the book, but what I have seen is an example of a two-step method. So m equals 2. Wait. Oh, it does satisfy. Yeah. Yeah, I have seen an example of a two-step method that is. Oh, I showed it to you earlier. Simpson's method. Simpson's method I showed you earlier is a two-step method because it goes back to time n-1. It's fourth order accurate, just like a composite Simpson's rule. It is weakly zero stable, but it's still zero stable. So it bumps up against that ceiling. So second order, so like if you had a case of the two-step method being somehow fifth order accurate, it could not be zero stable. And then the second barrier theorem said that there's no such thing as an explicit astable method. Only implicit methods can be astable. Also, high order accuracy and astability are incompatible. So I showed you an example of a first order method, backward Euler, and a second order method, implicit trapezoidal, that are astable. You cannot have a higher order accurate astable method than that. Also, the implicit trapezoidal method is, in a sense, the best astable method because the error is, it's order a squared, but constant in front of the error is the smallest when it is the implicit trapezoidal. So after that, the party's over. No more astability. Dang it. What I've also found when I've seen pictures of diagrams of regions of absolute stability is that the higher order accurate your method is, the smaller the region of absolute stability gets. So you're getting a higher order accuracy, but now it's a trade-off. Because you think, if it's a high order accurate method, maybe I get away with a larger h, because that h is being being raised to a higher power in the error. Well, yes, that's true, but you still have to use a smaller h to keep the method stable. So that's unfortunate. No free lunch here. Okay. So that's convergence analysis for you. How to show that a method is consistent and stable and therefore convergent. But aside from that, we do be concerned about stiff problems that you have to make sure that your time step is small enough so that the solution will exhibit the correct qualitative behavior. If the exact solution is meant to exhibit exponential decay, then you'll want to know something about your method's region of absolute stability. If you choose an H, run your solver, and get a solution that blows up, then you know your time step is too large. And unfortunately, a lot of real-world applications do have problems that are incredibly stiff. That's why MATLAB has a whole lot of ODE solvers. Some of those are classified as stiff solvers. For example, ODE 1.5s. The 1 and 5 refer to the fact that it uses backward differentiation formulas of orders 1 through 5. Those are all implicit methods. Since implicit methods are better than explicit at ensuring stability. So what ODE solver like MATLABs can do is try to get an idea for a particular problem. How large are the values of lambda under consideration? From evaluating the time derivative at various points, it can try to get an upper bound on lambda, and that can give an idea as to what h is supposed to be. Because the regions of absolute stability for these multi-step methods are all known. So we can try to choose an h that's guaranteed to work. But unfortunately, the larger value of lambda you get, smaller h needs to be. So the unfortunate thing about that is, as computers get more and more powerful, there's a demand for greater resolution in a lot of settings. So whatever equations you're solving, you're using finer and finer grids, spatial grids, than before. So now your time step needs to shrink to still be able to solve those problems. So you might think, oh, my computers are so much more powerful, I should be able to solve these problems so much more rapidly. But the opposite can be true, because you're having to use smaller time steps. So that's unfortunate. And that's a key driving force in my own research program, to try to preserve that scalability, that if you want more spatial resolution, that try to keep that computation time from increasing exorbitantly as a result. To try to develop methods, solution methods that are more scalable. I had to work at it there. Okay. So, are there questions about this or homework or? Yeah, I want to call it day 2. And so I will. All right, so we won't meet Wednesday. I will start with boundary value problems, chapter 13, on Monday.